Hi, everybody. I'm Pete, CEO at Dagster Labs, and today I'm going to be talking about the standardization of data pipelines. Just a little bit of background about me before we get into it. I started my career at Facebook, working on the React.js library, which became a very popular open source developer tool. I later was co-founder and CEO of a company called Smite, which used real-time stream processing to identify bad actors on the internet, which was acquired by Twitter. Spent some time at Twitter, ran a large org there, which included a bunch of data and ML engineers. And then finally, over the last couple of years, I've been at Dagster Labs working on Dagster. The prompt for my session was, if I could fix one thing in the data world, what would it be? And inspired by my experience with React.js, the answer is standardization. I'm going to talk through what that actually means, so why standardization matters in the data domain. I'm going to touch on the history of intermodal containerization as applied to shipping, which is a mouthful. Then I'm going to talk about how we can apply the lessons learned from shipping containers to technology. I'm going to talk about what hasn't worked for data pipelines, and then some potential paths forward. So kicking things off with why standardization actually matters in this domain. So when engineers plan for the future, I think they make a really common mistake. They plan for the median engineering project. So the 50% chance, the majority of projects that take the average amount of time, but they don't plan for what I like to call a P99 project. These are the 20% of projects or fewer. In the case of P99, it's actually 1%, but the 20% of projects that consume 80% of the resources and add 80% of the risk. One interesting property of these projects is that they tend to cross team boundaries. And so my thesis is that if you can standardize your cross-team work, make it easier to collaborate across teams, this will hugely accelerate P99 engineering projects and will thus accelerate your whole company. So I think this is really important and it really matters a lot. So let's talk about the history of shipping containers. This is how we used to ship goods back in the 1910s. As you can see, there's a bunch of different types of things that need to be shipped. There are barrels, there are crates, there are bags, and there are loose stones. These things all had to be packed and unpacked separately every time these goods were moved. So you'd pack them onto the ship. When they would arrive at the port, you'd unpack them, and then you would repack them onto a train. And then when they get to their end destination, you would unpack them from the train and onto a cart that goes to the final recipient. These days, we don't do a lot of packing and unpacking. We use standardized shipping containers, which has completely revolutionized how we ship goods across the country and across the world. So there are two big innovations here. The first is intermodality. So a shipping container can be moved without packing it or unpacking it between a ship, a train, and a truck, and even other forms of transportation. The second is that they're general purpose. You can basically put anything into one of these shipping containers, and there are very few constraints as to what can go in there. Refrigerated goods can go in there, large goods, small goods, etc. So if we were to apply this to technology, I would say we're not really talking about intermodality. We're talking about collaboration. So standardized abstraction, like a shipping container, can enable different technical teams to leverage each other's work. And the second is flexibility. So ideally, the abstractions that we would adopt cross-team would allow implementers to leverage whatever tools they want at an arbitrary level of complexity to accomplish a large number of different tasks, maybe ones that we haven't even thought of yet. And so let's talk about what hasn't worked for data pipelines. So there's really three problems with existing technologies that have tried to solve these problems. The first is collaboration, like I said. Collaboration between teams is done in a non-standard ad hoc way, which slows everything down. The second is flexibility. There are some standards that are adopted that help teams collaborate, but they're not flexible enough to really solve the real world problems that modern data practitioners have. And the third is product domain fit. So there are certain tools that do solve the collaboration problem, the flexibility problem, but they're not great for solving data problems. So when we're talking about containerization, you're probably thinking about Docker or Kubernetes. And so these are two very popular technologies that make it really easy to package up an application into something called a container and run it anywhere. They were designed primarily for generic backend development, especially web services, but you see them adopted in the data domain. So they're great for collaboration and flexibility, but they're a necessary but not sufficient part of the stack because they have poor product domain fit. So they're not designed for data pipelines. This means that there's no observability into the data that's being passed between tasks. There's no lineage between different containers that are processing data. Scheduling is done in a pretty inflexible way as well. So oftentimes people will adopt something like Apache Airflow, either in conjunction or to replace Docker and Kubernetes. And this is a tool primarily used for orchestrating data pipelines, but the core abstraction here is a task, which is a black box thing that runs a bunch of code inside of a Python process. Now, what we hear from users is that Airflow has the NPS of a chronic illness. It is not a universally loved technology by any means. It has poor collaboration and flexibility because tasks are so opaque. Sharing data between them is quite difficult. There's no code isolation. There's implicit dependencies between these tasks. And you have to write all of your code in a single Python project with the same set of dependencies. And the alternative is to shell out to different CLI tools or Kubernetes jobs and string together giant strings of command line arguments. Additionally, there's poor product domain fit. Even though a lot of data teams use Airflow, it still doesn't have great support for data observability, and there's extra work needed to get true data lineage, and that data lineage can often fall out of sync and is generally not a rich representation of that data lineage. And finally, while Airflow does support a bunch of different types of cron scheduling, it's still considered fairly inflexible when it comes to those types of scheduling behaviors. So I'd like to present a new way of thinking about the problem that we call software-defined assets. And we really came up with this idea, a year or two ago, and we've seen adoption throughout the industry, with Dagster and in other tools as well. So the big idea is to think about the problem declaratively, not imperatively. Said another way, think about the what, not the how, the nouns, not the verbs, or the data assets rather than the tasks. So thinking about the outputs, the thing that we're actually producing rather than the task that produces it, opens up a bunch of interesting and exciting possibilities. So what is a software-defined asset? The big idea here is that you co-locate code with the asset definition rather than have a black box task that can consume any number of assets and produce any number of data assets in a way that's uncontrolled. You infer lineage directly from the code without doing any additional modeling. Assets can have additional metadata attached, and it produces a bunch of different benefits. So from a collaboration perspective, software-defined assets adhere to a common interface, which means my team can produce an asset that is later consumed by a different asset, and we can all observe the status of each other's assets in a standard way. It's also flexible. The code backing a software-defined asset can do anything, be written in any language, and it runs in its own process or Docker container by default, enabling isolation. And finally, product domain fit, designed specifically for data applications. And so they expose rich metadata about the freshness of the data, the state of the data quality checks, and the lineage. So in terms of where we're taking software-defined assets next, we've recently announced a new protocol called Dagster pipes. So this really tightly integrates software-defined assets with external processes, and technologies like Kubernetes. And similar to how Airbyte introduced a protocol for connecting sources and destinations to produce, really great and robust extract and load pipelines, we've introduced Dagster pipes to take a similar approach to data orchestration. So I would really encourage you to check out the blog post that we have on software-defined assets and the blog post about Dagster pipes, because even if you're not going to use Dagster for your data pipeline, these ideas are pretty timeless, actually, and pretty flexible. You see the same ideas crop up in technologies like React and technologies like object-oriented programming. And so I think you can take this style of building and apply it to your own domain, regardless of the tools that you use. And with that, I just want to say thank you for having me today.